To get to the theme of our talk of today now, we will hear a great talk about detecting illegal small-scale mines in Ghana using deep learning. And this team will be presented by our speaker, Olivia Klose. Olivia Klose is software development engineer at Microsoft, and she's helping partners succeed on Microsoft's cloud platform, Azure, with a focus on analytics, machine learning, and deep learning. She's a frequent speaker at international conferences as TechEd Europe and PATH Summit. I'm very welcome and very happy to welcome you here, Olivia Klose, and thank you for being with us this afternoon. The floor is yours.
Thank you for the invite. Hi, everyone. As was mentioned beforehand, I'm Olivia. I'm from Microsoft, and I work as a partner or customer-focusing software development engineer. So the difference is a typical software development engineer at Microsoft works on a specific product, whereas I essentially, or my job is that I help customers use our technologies to enable their machine learning scenarios. So yeah, this talk here is detecting illegal small-scale mines in Ghana using deep learning. So very long title, so I'm super psyched that still so many people came here to this room. So just beforehand, a show of hands, who would call themselves a data scientist? Okay. So I see just like 3, 4 hands. So this one would probably be, or includes a bit of an introduction to deep learning as well. And then obviously the problem that we have tried to solve in this engagement. And then also show of hands, who has seen the movie Blood Diamond? Okay. So when I got involved in this project, this is the movie that I was always thinking of, like, oh, Blood Diamond, oh, this really sounds like something that we can actually change. Not like the typical Fortune 500, like, okay, how do we make more money, for instance? Disclaimer, I'm a total noob with regards to small-scale mining in Africa. But here's some facts beforehand. So this is what literally like small-scale mines look like. So almost like ponds or bigger ponds, and they don't really look like production ready as well. And then here's some numbers as well. So in Ghana, there are about more than 1 million workers in the mining industry, pretty much. And Ghana is the second largest gold producer in Africa. So sounds pretty impressive, but then on the other side, 1/3 of that produced gold is actually coming from small mines, and usually these are based on illegal mining activity. This project was actually brought to us by a university called Royal Holloway University of London. And the question that they asked, or this PhD student, Martin Günther, asked me like, oh yeah, so his PhD thesis is pretty much on the hypothesis that illegal gold mining in Ghana is harmful. So fact is, it is rampant, it's everywhere. But the question is like, what are the environmental impacts of such illegal mining activity? Does it also have, or does it harm, or does it help the locals? So the question with like helping or harming, does it actually have any impact on like, is there more higher level of child labor? Is there a higher level of prostitution in this area? Or also, are there any health risks? Because yeah, these are illegal, so or certain illegal mining activities usually doesn't really care about worker security in the first place, but then on the other side, you could see in the slide before and with the pictures that there were like fairly big ponds, and I'm not sure about you whether you've been traveling around, but I've been in India, and there was always the scare of like getting malaria or dengue fever because yeah, I'm not best friends with mosquitoes to say the least. So these were questions that this PhD student Martin actually had, but the issue with such, or with proving such an hypothesis is, well, we need data, and there's hardly any data because obviously if it's illegal, there's hardly anyone who's saying like, oh yeah, so our illegal mines are there, and there. So first issue, how to find such mines, and then the second issue is also having general environmental and demographic data as well, doing correlation with the locations of such small-scale mines or illegal mines, and then the demographic surveys that we've got. So the way that our team usually works is in what we call a hackfest. So it's not a hackathon in the sense that it's a competition and just like 48 hours where you don't sleep, you just eat pizza and then drink lots of Red Bull or coffee. Here, hackfest is more like, okay, it's a longer engagement. It's like 1 week engagement where we lock ourselves in a basement and pretty much try to get something working. And this was essentially one of those engagements that we had with the Royal Holloway University of London. So Martin, this PhD student, told me like how he has done it so far. So obviously the first issue is trying to find where such small-scale mines are. Not speaking of the illegal ones first, just the small-scale mines. And what he literally did was he went to Google Maps, activated the satellite feature, and then went through all of, or tried to go through all of Ghana. Usually those mines are located nearby rivers, so he went along the river and tried to identify, okay, this might look like a small-scale mine. Maybe it's also illegal. And then noted down the geo-coordinates. Obviously, it's very tedious, and Ghana is not such a small country. It's about like 2/3 of Germany. So we're like, maybe we can help you with that, help accelerate that work. So here, Bing to the rescue. So I'm from Microsoft, so obviously we have resources from Bing Maps, and we're able to get all those like the high fidelity image or satellite image tiles from Ghana itself. And then the question is, well, as you know, like if you zoom in or zoom out, there's obviously different levels of resolution. So what is the right resolution? So with just some playing around, I think there are like zoom levels like up to 25. We decided to go for like a zoom level 18. So it's sort of like in the middle. And then also we just had 1 week to do that. So we didn't want to cover all of Ghana. So what we decided to do was just focus on the southern area of Ghana first. And just because Martin, the PhD student, told us like, okay, yeah, he has noticed more mines in the southern region, but then again, this also introduced a little bit of, or not a little bit, but yeah, some bias into our model as well. Something that needs to be improved. So okay, we have image tiles or satellite image tiles from Ghana. And what we wanted to do was literally like the hot dog, not hot dog app. Who knows or who has seen the series Silicon Valley? Okay, you have to see it because there's one very funny scene where they hired a developer and said like, oh yeah, you need to build an app for us which says like whether it's a hot dog or, and they thought like it would identify any other object, but essentially the developer understood, okay, hot dog, not hot dog. And essentially this is what we wanted to do with the mines. So we have an image tile or satellite image tile, and then it should say, the models should say, okay, there is a mine or there's not a mine. Sounds simple. Here, a screenshot of like some of the image tiles that we have. So not mines looks like, okay, looks just like forest pretty much, but then surely there must be some land on Ghana that is not forest and not a mine either. So something that should be investigated as well. Here with mines, we can see like here in this image tile, there's a big like pond or like one of the bigger small scale mines. Here there are like about 2 of them or 3 of them, and so on and so forth. So this was the idea of this project, and it makes you think like, oh, okay, so this is image classification or image recognition. Let's do a quick detour what I actually mean with image recognition or what image processing has gone through in the last few years. Because it's not really that simple with a computer to do image recognition. For us, it's super easy, but then computers take everything very literal. So I remember I joined Microsoft about 5 years ago, and before I joined Microsoft, I focused on medical imaging. And the idea there was, okay, we have all those MRI, CT scans, and you want to identify whether there is a tumor in that image as well. And there it was all about, that was before the age of deep learning. And I remember when I talked to my supervisor and asked him, oh, so how about neural networks? Because we've just done it in some lectures. And then my supervisor said, it's so 90s. Forget about the neural networks. Fast forward 5 years, neural networks, or the new wording, deep learning, this is something that everyone is talking about. The issue that we had like up to 5 years ago was the process and image processing has sort of stagnated because it was always about just finding the right features. So figuring out whether we can do an edge filter, oh, okay, this doesn't work out, try to do some further feature engineering. So a typical filter that has been used back then was that Sable filter, which essentially just shows us the edges of a picture. And then also another feature could be the colors and histogram of gradients and so on and so forth. But the thing is, like, it's always down to the features that you use, not really about the model itself. And then 2012, there was pretty much the big bang with deep learning. The thing is, deep learning is not really new. Deep learning is something that Jan LeCun, for instance, has already written a paper on in the 80s. And I also read an article where it was about, if you were writing or submitting papers that used the word neural networks, it was pretty much like a dead end. Like, you were never going to be accepted to a conference as well. So what has changed? Why is deep learning suddenly such a big thing? And I like the analogy that Andrew Ng has once given of deep learning. So deep learning, a lot of people always think that we are trying to imitate the brain, but the thing is, like, our brain is so much more, so much bigger than any deep learning model can ever be. So a better analogy is a deep learning model is something like a rocket ship. It needs a lot of fuel, hence a lot of data. It's also very complicated, hence the model has lots of layers, needs a lot of engineering power, or engineering brains pretty much, to build, which means, like, that model has a lot of layers. And with cloud computing, this is where we have all the compute now or the compute power, and in the age of internet, we have a lot of data as well. So that's the reason why deep learning has suddenly become so big. But essentially, deep learning is just a neural network with lots of layers. And I've heard a story, and I'm not sure whether it's true. The reason, so it's a very, like, typical marketing thing to do, like, oh yeah, just let's rename it, and then it's going to become popular. And the reason why it's being called deep learning is because then all the other models can be called shallow. Let's see whether it's actually true. But we can see that the first, or 2010, 2011, this is still where, like, the shallow models were still very much in trend. And then 2012 is where AlexNet, the first deep learning model in the computer vision area, has been applied and then won that particular competition. And then the layers, or the number of layers, has increased dramatically, and then also the error rate has decreased quite a lot. So just a short recap. So what is the difference then between machine learning and deep learning? Machine learning, it's all about, like, okay, getting as much domain expertise as possible beforehand, and then figuring out what the right features are for a model. Versus a deep learning model, which is pretty much just like give all the relevant data, but and the deep learning model will figure out from the data itself, okay, what features are sort of relevant. And this is a screenshot that I've shamelessly taken from a conference talk from the NVIDIA conference. I would highly recommend watching the talk that I've referenced down there. So how does it work with, like, a human or a brain of a kid? So essentially, and this is the way that a deep learning model would essentially work as well. So the kid or the human sees a dog and first tries to extract, like, certain abstract features. And these are low-level features. And then as we advance, this becomes like a more complicated or more complex feature. And this is what a deep learning model looks like as well. We can see like at the beginning, so there are a couple of layers. I'm not going to go into detail because we only have half an hour. But yeah, here we see that there are only like straight lines in the first layer, and in the second layer, they become a little more rounded. And then as we further progress, those features become a little more complex with like multiple lines crossing each other, for instance. So for instance, just like what does a model see when it sees a dog? These are the various features that it sees like per layer. And we can see like some of them are just simple edge filters, and then later on they become a little more complex or more complicated, which resemble more the picture of the dog. And then when we reverse it, when we ask the model, what does a dog look like to you? This is what really creeps me out then. This is something that a Google researcher has come out with. But the thing is, the model knows, okay, a dog must have 4 legs, a nose, two eyes, but doesn't know that, I mean, the nose could be mistaken for like 2 eyes as well, and therefore there are more dogs or dog faces appearing out of it as well. So that was a little detour. So how does it apply to the MIND project? And this is where we applied transfer learning. Transfer learning essentially means, okay, there are all those like super smart researchers that have already built those models. We just take those models and use it for our data set. And this means that we just like extract or take away the last layer and then add or massage that model into our data set. And in such a way, we don't need 1 million pictures to train our model. Maybe just 1,000 pictures would be enough to train it on like dogs or to train it on mines and so on and so forth. Oh, yeah, and a shameless plug for Microsoft as well. There's a service called Custom Vision Service, which is pretty nice because you can easily drag or upload your own pictures. You don't even have to like build your own model. And this essentially, or under the hood, is using transfer learning. So going back to the mines, what did we do? So we have, just a quick reminder, we have about 6,000 images or image tiles from Bing. We want to split it up into 3 data sets: training, testing, and validation. The reason just because we want to use the validation data set to check like, okay, we've run this through our model once, want to tweak the model a little bit, and then train it again. And then the testing data set is something that we are going to use at the very end to see, okay, how good was actually our model. Then here we are training the model, and yeah, it has a couple of features that, or a couple of parameters that have also been mentioned or have been shown in the slide with all the layers. And then in the end, we want to score it. We want to evaluate it. And there we use confusion metrics. As a deep learning framework, we use Keras. So for anyone who wants to get started with deep learning, Keras is the way to go because it's so intuitive as well. And unless you want to go for like performance, then you might want to go for like TensorFlow or CNTK and so on. But Keras is quite nice to get started with. And it already has, out of the box, a couple of those models already saved or stored. And by models, I mean like the models that those super smart researchers have built on for their specific image processing competitions. And here are 4 of them, like a very popular one is called Inception v3 at the moment. So okay, it sounded like fairly easy, but then here are a couple of hidden dragons or like pitfalls that we fell into. So the first one is, so we just used it and then, or we just trained the model and then we realized, interesting. As soon as a tile is green, it always says like it's not a mine. I mean, obviously if it's just like this sort of data and therefore it just made it like a green or brown-green classifier. As soon as it's brown, it's going to be a mine, which wasn't necessarily the case because there could be areas where there is not a mine and also not a forest. So we had to we had to adjust the model a little bit or improve it, and we did it by data augmentation. So in other words, we used those 6,000 image tiles and then rotated them, zoomed in, did a little sharing as well, and then flipping it, because in the end, like, it doesn't actually falsify the result. If this image is just being flipped, then it's still not a mine. So we just increased the data set in such a way. And then the next one is we introduced a third category, because turns out there are quite a lot of satellite images with clouds on top. And therefore, we can't actually say whether it's a mine or not a mine because it's covered. So we had to introduce a third category, which is the cloud. Then looking at the, okay. So we built the model. How do we put it in production? So here in the Azure files share, so this is all running on our cloud platform. This is where the Bing image tiles are stored. The location of each image tile is actually indicated by a quad key. So we had to decode it to say, like, okay, which longitude and latitude is it in? And then in the end, we apply the model to actually predict, and then the result was stored in a MySQL database. The result was not too bad. So this is the confusion matrix, and the result, or the thing that you want to reach is that the diagonal is as dark as possible, or like has as high, or has numbers as high as possible, which means, like, okay, those image tiles have been correctly classified. Well, I guess, like, quickly, just like the last 2 minutes, I want to take, because another question that we had was, okay, what impact does it have? And the thing is, we had a lot of data sets, but too many features, so like 700 columns, which was super, which didn't really provide a good overview. And the idea was, we thought, like, oh, okay, there might be a correlation between the locations of mines and malaria cases, for instance. Turns out, no, it's not the case, or we don't have the data, or we don't have enough data, because this is where the mines are located that we have identified so far, and this is where all the malaria cases are, or here, incidences of fever. So it was still fairly inclusive, not conclusive. Or the last one, or another one that we tried to find out is, like, okay, are there any other correlations to be found? The only correlation that we could find was that small-scale mines are fairly nearby large-scale mines. So trying to sort of copy or get some advantage from some neighboring large-scale mines, or like the proper mines as well. I guess with that, I can sort of stop, because, yeah, we are running out of time. If you have any questions, I'd be happy to hear.
Okay, thank you very much, Olivia. Thank you so much. We have now a short, tiny question and answer session. Please raise up your hand, so I will come over there. We will only be able to answer 2 or 3 questions because we are running out of time, but I will try to get a good mixture up. So we'll guess on the last, and afterwards I come forward.
Hey, so my name is Haluka. I'm a news developer and data journalist, and what I was a bit interested in at the end, you showed this, that you looked for different correlations, right? And I was kind of wondering, I mean, if you look at enough variables, like, you surely will get just by chance something that correlates with the other thing. So what is kind of the process of you like avoiding that you just run into some kind of p-hacking, that like just by chance you will something that correlates and just got like, hey, turns out like malaria also, mines also correlate with, I don't know, barbershops, where it's like, okay, well, there is probably not really like a logic, deterministic reason for that.
Yeah, that's a good point. The thing is, to be fair, like we only had this 1 week where we were trying it out. And the thing is, like, this is actually the thesis of that PhD student. So, I mean, it would have been like a big surprise if we did manage to find something within that 1 week. And there, to be honest, like before we started off, we already had our doubts whether we have the right data sets, because some of them are not really connected properly. They're supposed to be taken like every 7 years over a time span of like 21 years. But then if they always ask the like different people, the thing is, yeah, what I wanted to show is just like, okay, we still have to have some way to go before we can actually make any proper conclusions about that.
Okay, one more question, short and simple, we can accept. Who wants to ask? Yeah, come over there.
So how many illegal mines did you find at the end?
So the thing is, like, we can't say that we have found illegal mines, because yeah, that would be ideal. But yeah, I think we just found, like, I don't know, 2,000 more small-scale mines. The thing is, like, it's still ongoing work that because we've only focused on the southern area. So now, like, it would be, yeah, we want to look into the like northern area of Ghana as well. I guess another interesting thing is, like, okay, once we do find out about it, what do we do with the findings? So if anyone has any contacts to Ghana, we'd be super happy to hear about it and like do a proper follow-up on that engagement.
Okay, thank you to you all, and thank you, Olivia.
Yeah.